Okay, subatomic particles. So we've learned about the discovery of the electrons and the ideas about what the nucleus is. Now we're going to look at what those particles inside of an atom are. All atoms are composed of the same three particles. Protons, where's my pointer? There it is. Protons, neutrons, and electrons. Protons and neutrons have nearly identical masses. So here's the mass of a proton, the mass of a neutron. They differ in the fourth significant figure, right? Very, very similar. 10 to the minus 27 kilograms. That's a decimal point and 26 zeros, 1 kilogram, right? Crazy small. The mass of an electron is even smaller, 10 to the minus 31 kilograms, okay? And just to give you an idea of the relative sizes of these things, and by the way, for our purposes, we can consider the proton and the neutron to have the same mass. We're not going to worry about these little differences here. And these are numbers that you do not need to memorize, okay? Here we have a picture of a baseball and a grain of rice. So if this were the proton, an electron would be the size of a grain of rice. So the electrons are much, much smaller than the protons. And, when we're talking about the bigger picture, we often consider the electron to have no mass, okay? And you might say, well, how could it have no mass? Well, when something is so small relative to the rest, it just doesn't matter. So I live in Reedley where we have a lot of fruit being grown, and so we have lots of semi-trucks running around. And there's a public scale, and the trucks have to weigh. And so you come in and you got this big load of peaches, right? And they get on the scale and they weigh the truck and they're going to drive away, and a guy comes out from the packing house, wait, you forgot this one. And he tosses it up there. Do they need to re-weigh the truck for one peach on top of a whole truckload full? No. Does that peach have no mass? No, it has mass. It's just so small relative to the mass of the full semi-truck that we can just say it's negligible, doesn't matter. That's what the electrons are like. They do have mass, but it's so small relative to the protons and neutrons that most of the time we just say, it doesn't matter. I'm not thinking about it. So as we can see here with these crazy numbers, kilogram is not a good unit for measuring the mass of something this small. Even something like nanograms, picograms, not going to help very much. So we have a special unit for measuring atomic masses, and it's so cleverly called the atomic mass unit. How's that? So we created a unit, and that sounds a little flip, but all units are man-made, right? Units are not an intrinsic thing. We made up all of the units. So we use the atomic mass unit, which is abbreviated AMU. That's not some weird cousin of an emu. We just call it an AMU. And it is defined as 1/12 the mass of a carbon atom that has 6 protons and 6 neutrons. And that definition is significant only in that the way these things were defined was for ultimate convenience. So what that means then, if this atom has 6 protons and 6 neutrons, and 1 AMU is 1/12 that mass, that's basically saying that 1 AMU is the mass of a proton or a neutron. It's not exact, but it's very close, and for our purposes, it's good enough. So you can think of proton or a neutron as about 1 AMU, atomic mass unit. So the charge of the proton and the electron are equal in size, in magnitude, but they're opposite in sign. So the proton is positive and the electron is negative. And we have measured their actual charges. So proton is this number in coulombs. electron is this number in coulombs. It's the same number, it's just negative. They're exactly opposite. We don't need to know these numbers. They could possibly come up in some odd problem that I would give you in a worksheet or something, but you would not need to know those. What we do need to know is the relative charges, and those are so much easier. A proton has a relative charge of +1. A neutron is neutral. You can go ahead and slide that door closed if you want. He can get kind of loud sometimes. Neutrons are neutral, so no charge, and an electron has a -1 charge. Okay, that's important. We need to know that part. There are the masses in kilograms. Again, you might need to refer to this chart for a problem, but you don't need to memorize those. Here are their masses in atomic mass units. And as we can see, the proton and the neutron are very, very close to 1. And so most of the time, all we need to do is say is 1. And the electron is about 1,800 times smaller. And so for most of the time, we can say that's approximately 0. So let's use a different color here. Maybe red would be good. So this is approximately 1, approximately 1, approximately 0. And these are the numbers that you need to know. Okay? That's not too bad. It's 1s and 0s. Any questions? Now, matter usually doesn't have a charge on it because protons and electrons are normally present in equal numbers, and so we don't have a net charge. When we do get a net charge or a charge imbalance, it's not stable, and those charge imbalances usually equalize themselves quickly with no influence on our part, and it often happens in rather dramatic ways. Lightning is an example. Lightning is an equalization of negative charge building up on the clouds and positive charge building up on the ground. And it gets to this tension and crack, the thunder and lightning, right? The lightning comes and you hear the crack from the thunder, and that's the charge equalizing. Static electric shocks are another example of that. When the air is very dry, especially if you're wearing socks and you're shuffling on the carpet and then you touch something that's metal, you get a little shock, right? Or you rub a balloon in your hair and it makes static electricity. It equalizes itself. So these opposite charges do not like to be separated from each other. So atoms have protons, neutrons, and electrons. The number of protons in the nucleus of an atom is what determines which element it is. So elements are defined by their numbers of protons. This is called the atomic number, and it's given the symbol Z. Oh, there's the reason. It's from the German Zahl, meaning number. Because I always thought that atomic number really should have the symbol A. Because mass number is A and atomic number is Z, and that just seems like crazy backwards to me. But apparently there is a reason. I wrote this on the slide. I guess I deleted that from my memory bank. So if we look at helium, here's a helium balloon. Inside the nucleus of a helium, there are 2 protons. All helium atoms have 2 protons. That's what makes them helium. So the proton is a little bit like the personality or the soul of the atom. I like to personify things. It makes things more interesting. So I think of the number of protons as your intrinsic being, who you are. As people, we can change what we look like, right? We can put on different clothes. We can take clothes off. We can even alter our bodies in various ways. You can cut all your hair off or do different things. Does it change who you are? No, you are still you, whether you like that or not. So the number of protons doesn't change. That's the personhood of the atom. Here's carbon in the graphite pencil. Inside every carbon nucleus, there are 6 protons. Always, always, always. On the periodic table, we have the elements listed in order of atomic number, the number of protons. So when we look at each of these squares, you're welcome to take that chair or that stool, whichever's more comfortable. Inside this box, we see the chemical symbol for the element. This periodic table has the names on it too. And above that is a whole number. The whole number is the atomic number. That's the number of protons. So for beryllium, beryllium atoms have 4 protons. And you could go find anything in here. Here's tin. Tin atoms have 50 protons. So that information is right there in the periodic table. Any questions? Periodic table is a really, really useful thing. It's sort of a symbol of chemistry. And on an exam, you will always have a periodic table. It's not going to have the names of the elements on it, but you're going to have a periodic table. It'll be very similar to this one, and the one on the wall is always going to be there. We don't memorize the periodic table, but we need to become familiar with it and be able to find things on it quickly. So each element, of course, has a name, but it's also identified by the unique atomic number, the number of protons, and a unique chemical symbol. Okay? I've already made you memorize these and tested you on it, and most of you did pretty well on that quiz. So the chemical symbol is either a 1 or a 2-letter abbreviation. 1 or 2. The first letter is always capitalized. If there's a second letter, it is never capitalized. And this is where we need to be a little careful with our handwriting. So we need to be careful when we write these abbreviations. Sometimes people like to write in all caps, and they use small caps, and so you might want to write the abbreviation for tin like this, right? That's not acceptable to me. This is a capital N. I don't care how big you make it or how small, it's still a capital N. So that's not okay. So it's SN. Okay, and aluminum, this comes up sometimes. Sometimes people do that. It's not a L, like initials. It's a lowercase l, okay? So that's not okay, because a capital letter is the beginning of another element, okay? All the rest of the words that you write, I don't care. You can write in all caps or whatever. But element symbols have to be correct. And then there's also an issue with, some letters look the same. It's only their size that differentiates uppercase and lowercase. So O is an example of this. So that's cobalt. And if I make my O too big, that's carbon monoxide, right? So we need to be very clear. With typing on a computer, it's not really a problem, except that L's and 1's and lowercase or capital I's sometimes look the same. And mastering chemistry does know the difference. But when we're writing things by hand, we need to be very careful and aware of that. So I know some of you write, my boys have horrendous handwriting, so I totally get that. But they can write well if they need to. It's just really slow. So just slow down when you get to the symbols and then go back to your sloppy, okay? That's fine. Now, a lot of the element symbols make sense, like HE for helium or C for carbon. It's the first 1 or 2 letters of the name. Some of them, like, which ones? Now I'm blanking. Oh, manganese and magnesium, right? Neither is MA. One is MN, one is MG. And so they skipped the second letter and went to the third letter because that's the first letter that's different. Okay, so manganese and magnesium. But others don't seem to make any sense. So sodium doesn't have an A or an N in its name at all, but its symbol is Na. And that's because it's from the Latin natrium. So some of them are based on Latin or even Greek names, and we kept the symbols because those names had been used for so long. And so we just have to deal with it, okay? But there's a reason behind the ones that seem weird. Any questions about those element symbols? Okay, so one of the things that Dalton said in his atomic theory was that all atoms of a given element have the same mass, and basically they're identical to each other. We know that's not quite true. All atoms of the same element have the same number of protons, but they do not necessarily have the same number of neutrons. The number of neutrons can vary a little bit. So we have a name for atoms that have the same number of protons but a different number of neutrons, and these are called isotopes. The prefix iso is a prefix that means the same. So they're different, but they're the same. So isotopes. An example, neon. So all neon atoms have 10 protons. But some of them have 10 neutrons, some have 11 neutrons, and some have 12 neutrons. All three of those types or isotopes of neon exist. If they have a different number of neutrons, then they cannot have the exact same mass, right? Because protons are 1 atomic mass unit, neutrons are 1 atomic mass unit. You add an extra proton, you change the mass. And so we had to adjust that point in Dalton's atomic theory a little bit. Now you cannot predict how many neutrons an atom has from the periodic table. The number of protons is up there. The number of neutrons is not something that's easy to predict. And, you know, how do we know that neon has 3 isotopes? How do we know it's not 4 or just 2 or what? Some atoms don't have any isotopes. Some have several. It's by experiment. You have to actually look at the element with sophisticated equipment and do experiments and figure it out. And so, of course, people have done all that already for us. What we find is that the number of neon atoms with 10, 11, and 12 neutrons is not the same. If you take a sample of neon, it's not split equally in thirds. It's some other distribution, but that distribution is quite constant no matter what sample of neon, no matter where you got the sample of neon. And that distribution is called a natural abundance. So, you know, you might have 10% of one and 90% of the other for a given element. And it's always that. Okay, that's the relative, that's the natural abundance. And we'll get to that a little more in a minute. So we can specify that a neon atom is neon by just, you know, capital N, lowercase e. But how do we tell the difference between these 3 isotopes? We use nuclear symbols. So here's the symbol. We use the chemical symbol. That's just the abbreviation from the periodic table. And to the left, as a subscript on the left, we have the atomic number. That's the number of protons. And then we have the mass number as a superscript on the left. The mass number is the number of protons plus the number of neutrons. It's the number of massive particles in the nucleus. And so the mass of that isotope will be approximately equal to the mass number in atomic mass units. So those 3 isotopes of neon that we've been talking about, they all have, my pointer doesn't work down there. It's so annoying. Dang it. Okay. So the first one, with the 20 as the superscript, that's the mass number. I'm going to draw it up here because I need to. So neon, it has 10 protons, and this one has a mass number of 20. That means protons plus neutrons is 20. What if I want to know how many neutrons there are? Well, I have to subtract the number of protons. So we've got the number of protons here, the total number of massive particles here. If you want the neutrons, you subtract. And it's kind of just stacked up like that. So the second one, 21 minus 10, would give us 11 neutrons. And the third one, 22 minus 10, would give us 12 neutrons. That's how I remember that the mass number goes on top and the atomic number goes to the bottom. Because if you did it opposite, you couldn't subtract. You'd get a negative number, and that's not possible. So we can use a symbol like those guys to indicate which isotope we're talking about. Another way, because that sort of a symbol is a real pain to do on a computer, those stacked superscript subscripts, you have to get out the math editor and put an equation in there. It's a real pain in the neck. So there's two other ways that are much simpler. One is to use the chemical symbol and a dash with the mass number. So Ne20, that's a real short way. Or we can use the actual name, neon 20. And if you're saying it out loud, you'd probably just say neon 20 even if this was written. Neon 20 tells us that 20 is the mass number. It's not giving us the atomic number in this name. But we have a periodic table. No decent chemist will ever be without a periodic table. I have a periodic table app on my phone. It's very comforting. And then there's my cup too. You know, this goes everywhere. So I can tell how many protons there are. It's on the periodic table. But I don't know how many neutrons, and so the mass number is important. Okay, any questions? So again, looking at these three isotopes of neon. These are the symbols. Each of them has 10 protons because they are neon. All neon atoms have 10 protons. But they have differing numbers of neutrons. When we add the protons plus the neutrons, we get the mass number. So 10 plus 10 equals 20, etc. Yes?
So consistently an element will have a set number of isotopes?
Yes. Okay. Yeah. Elements have whatever number of isotopes they have. Okay. And it's seemingly random. There might be some pattern.
It's consistent.
But it's consistent, yeah. Neon will always have 3 isotopes. And so whatever sample of neon you get, it's going to have 90.48% neon 20, 0.27% neon 21, and 9.25% neon 22. Okay. We have learned that these natural abundances can change a tiny bit, but for our purposes, that's not at all significant. So the natural abundance of these is going to be the same. This also is not predictable from the periodic table. And so if you need it in a problem, we'd have to give it to you. Or we would give you the information needed to calculate it. Okay? So let's do a little practice here. So there's a periodic table because we need that. First question, what are the atomic number, the mass number, and the symbol for the carbon isotope with 7 neutrons? Well, how do we find the atomic number for carbon? We just look on the periodic table. Here's carbon, and so it's 6. So the atomic number is 6. And what's the symbol for the atomic number? Z, not A. So Z equals 6, 6 protons. Mass number. So the mass number is the number of protons plus the number of neutrons. The question gives us the number of neutrons, because otherwise we wouldn't know. So the mass number will be 6 plus 7. The mass number is A. So that's the 6 protons plus the 7 neutrons, which I believe is 13. And then the symbol. There's actually 3 different ways to write the symbol. On a test, I'd probably give this as a multiple choice question. And so you wouldn't have to choose between one of the 3 correct symbols. I'd give you one correct one and a bunch of weird ones. So we could call this carbon, and we put the atomic number at the bottom and the mass number at the top. So that's one symbol for this isotope. It can also be called C-13, C13, or we can call it carbon-13. Any questions? So how many protons and neutrons are present in an atom of this? If I had to read that, I'd call it potassium-39 or K39. Well, how many protons are in there? 19. We actually don't need to refer to the periodic table here because the number of protons is this number on the bottom. So 19 protons. And how do we figure out the number of neutrons? 39 minus 19. So it's all stacked up for us. And feel free to do that on your calculator. It's a shame to just have a brain fart and do simple math incorrectly. But I'm pretty sure that's 20. 20 neutrons. Any questions? So the number of protons is fixed. Each atom has its own particular number of neutrons, but that can vary slightly within an element. And then there's the electrons. So the protons and neutrons are in the nucleus. They're in the center. They're the core of the atom. The electrons are on the outside. I think of them more as like your clothing, your appearance. That's something that can change. So the number of electrons in a neutral atom has to equal the number of protons because it's neutral. We have to have an equal number of positive and negative charges. But in some chemical changes, atoms can lose or gain electrons. And when that happens, they have a charge. Okay, this is like taking clothes off or putting clothes on, make yourself look different. And we'll learn why they do this. For now, we're just going to say they do it. So a positively charged electron, I'm sorry, that's not possible. A positively charged ion, such as Na+, we put that plus up there to indicate that it has a charge. Positive ions are called cations. Positive ions are called cations. Negative ions, such as F-, there it's got a negative charge, those are called anions. Okay? I remember this because I like cats. I have positive feelings for cats, so cations are positive. If you don't like cats, well, this one has an extra N in it, and so that's the negative one. Somebody had a great one they told me last spring, and I forgot. But if you go look at this video from last spring, it's probably on there. Cations and anions, not cations and anions. Okay.